we have talked about different efficiencies such as volumetric sweep efficiency, aerial sweep efficiency, and these all efficiency altogether result into recovery factor. So we have discussed each of these terms in a brief way. Now also EV and EA will collectively referred as volumetric sweep efficiency. So if we talk about displacement efficiency, there's the first thing which we can say that recovery factor after water flooding is associated with displacement efficiency, which is true, and displacement efficiency is also associated with one of the very crucial parameter, which is saturation. Now there's one analogy you can make that on increasing the saturation of water, our displacement efficiency will increase, right? Because this is some sort of container. Your reservoir is some sort of container, and as you are filling up your reservoir with water, the oil is getting displaced, saturation of oil is getting reduced. So we can conclude that on increasing the saturation of water, efficiency of or displacement efficiency will increase, and ultimately recovery factor will also increase. So we can say that saturation is one of the most crucial parameter around which the whole picture of water flooding revolves around. So in order to understand the saturation profile and saturation dynamics, that is the profile of saturation with changing time, with changing the type of flow, and by changing the petrophysical parameters, there is one theory which is called as frontal displacement theory. So this theory was developed to explain the idea of saturation while and after, during and after water flooding. So this frontal displacement theory is defined by two components. First component is fractional flow equation, whereas the second component which you have is frontal advance equation. So these two equations define the saturation profile in a reservoir, and we will talk about fractional flow equation today. So what can you understand by the word fractional flow? Fractional flow is a type of flow, and it is defined by a variable f. Now fractional flow for any fluid will be the flow rate of that fluid in a container or in a reservoir in presence of other fluids. So fractional flow is sort of ratio of flow rate of water divided by flow of fluids in the reservoir. So basically we have oil and water system in most of the cases where we perform water flooding. So we can say that fractional flow of water will be equal to QW divided by QW plus QO. Similarly, fractional flow of oil can be written as QO divided by QT, and once you add up both of these terms, they will sum up to 1. So FO will be equal to 1 minus FW. Now in order to understand the whole concept, the whole picture, we take a part of our reservoir, and this is a reservoir. This blue lines are well, this is your injector well, this is your producing well. L is the length of the reservoir, A is the cross sectional area, and H is the thickness of reservoir. So reservoir is a porous media, and the flow of any fluid in the porous media is well defined by Darcy's law equation. So once you inject the water will displace oil, and both of them will flow in this direction. So with the help of Darcy's law, I hope we have completed the introduction of fluid flow through porous media. Now in this case, this is the flow rate for oil, this is flow rate for water, and basically in this equation we have two components, pressure differential component and gravity component. So if we draw another diagram of the same block, this diagram is not horizontal, it has some amount of dip. So alpha is your dipping angle, and basically it is the angle of this bed with the horizontal plane. Now because of this angle, there will be two forces regulating the flow. First will be pressure differential and another will be effect of gravity or potential difference. So Q naught here is given by minus K naught by mu naught into A. K naught is permeability, effective permeability of oil. This is viscosity of oil, and this is the pressure differential in case of oil, and A is the area of cross sectional, as I have told you. So this portion is due to pressure differential. This component, this term defines pressure differential, and this term defines development of flow rate due to change in potential difference, and alpha is your dipping angle. Similarly, we can obtain the same equation for water. Effective permeability, viscosity, pressure and density of the fluid will change, but the main structure such as A and alpha, it will remain same. Now once we have these two equations with the help of Darcy's law, now we will rearrange this equation. This will be taken to the left hand side. So once we rearrange this equation, this is what we get. Now let us mark this as equation 1 and this as our equation 2. Now we will reduce equation 1 from equation 2. So we will get QW mu W divided by KWA minus so you can derive this thing along with me, it would be better that way. And some of the equations in Tariq Ahmed have been derived wrongly. So once you go through those derivations, make sure that you are deriving those equations by yourself also. You are verifying it. Now here we have I hope you have noted down this portion. You can pause the video and note down this whole portion. So we can also rearrange this as this, and this is the difference in density of displacing and the fluid which is getting displaced. So we have seen earlier that QW can also be written as FW into QT. QO can be written as FO into QT, or 1 minus FW into QT. So once we take these terms and displace it, and what else can we change? Now this thing can be written as collectively Tx minus Pc is your capillary pressure. Capillary pressure is the difference between pressure in non-wetting fluid minus pressure in wetting fluid, so which is our oil, and wetting fluid is our water. So we can replace this whole term by del Pc by del X. Now let us replace these terms. We will get FW by KW mu W minus 1 minus Fw into mu O divided by Ko. Area and Qt can be taken out. It is the common factor. And on the right hand side we have dPc by dx minus G delta rho into sine alpha. Now we can take common out Fw from two terms as well. Negative negative will become plus, and there will be one more term. And also all these variables are in Darcy's unit. Let me check if this portion is visible or not. Alright, so this can be taken out here. My handwriting looks really bad when I just saw it in the camera. So this is the equation. Now I'm rubbing this portion. You can pause and note down. So what we'll do next, we will divide the whole equation by mu naught by k naught. We'll divide this whole equation by this specific term on both the sides. So here we will have when we divide this by this, what we will get? Ko by mu, this will become 1. Similarly this will become 1 again, and this portion is getting divided in this term. So again we will have k naught in the numerator, area divided by Qt, and this is what we will have. And we will take this term this side. So this is the final fractional flow equation when in Darcy's unit. So Darcy's unit will basically mean fractional flow is basically a ratio. Its unit will not matter that much, but still it will be in terms of centimeter cube divided by centimeter cube, and permeability is in Darcy, area is in centimeter square, viscosity is in centipoise, and flow rate is in terms of centimeter cube per second. Pressure will be in terms of ATM divided by centimeter. So pressure differential component is ATM per centimeter, but pressure will remain in terms of ATM. And this is the gravitational constant, centimeter square per second, and the density is in gram per cc. So these are the units, and this is the final fractional flow equation in Darcy's unit. Now in the fluid flow through porous media, you might have studied of unit conversion. If you have not, then you can mail me. Now in order to convert this equation into field unit, and also remember always that SI unit and Darcy's unit, the equation always remains same. There's no constant here. Same thing will happen in SI unit. And I think you will study that portion in unit conversion. And unit conversion is one of the most important part of GATE, because you cannot simply convert at the time of examination. So practice of unit conversion is very important. Now what happens in most of the cases, that effect of change in capillary pressure with, what do we call it, length, is not much, it is negligible. So dpc by dx can also be written as 0. And we will have this is 0.433. So this is the final fractional flow equation in field units. In this case, fractional flow will be BBL per BBL. K will be in terms of millidarcy, feet square, area. Density will remain same, only G will change. And this is minus 0.433. So this will remain as it is, gram per centimeter cube. This QT will be in barrel and viscosity will be in terms of centipoise. And this is the fractional portion, so we are not much concerned with that part. And moreover, you can extend this equation. You can extend this equation by writing effective permeability as absolute permeability into relative permeability. So this can be written as KRO into K, and this can be written as KRO by KRW. KK will get cancelled out. So this is another way to write the same equation. Now this equation is defined for water. The generalized equation for any displacing fluid can be written as FD, where D is your displacing fluid and FD is fractional flow due to fractional flow of the displacing fluid. Displacing fluid can be any fluid. And I'll write it down in terms of Darcy's law equation. Sorry, I will write it in Darcy's unit. Now this QT can be replaced by injection rate, because injection rate is the only thing which is pushing the fluid or responsible for any kind of movement in the reservoir. So we will replace this with injection rate of displacing fluid into minus 4.33 rho D minus rho oil into sin alpha divided by 1 plus mu D divided by mu O into KRO divided by KRD. So D is any displacing fluid, and this is the generalized equation. Now what will happen in case of gas? In case of gas, this term will become negative, but in case of water, this difference will remain positive. Now, first of all, before further discussing about that part, let us understand the concept of fractional flow and why is it important. So, fractional flow of any fluid, let's say water, higher the fractional fluid, worse it will be for us, because for example, fractional flow of water is high, then a large amount of water is flowing from injector to producer well, and hence what will produce? Large amount of water. If fractional flow of water is less, then fractional flow of oil will be greater, and therefore we can say that if the fractional flow of oil is greater, then large amount of oil is flowing towards the producer well. So we can say that our main objective while doing the water flooding operation is to reduce the FW value, water cut value. So you can note it down that main objective of studying the fractional flow equation is to reduce FW, or fraction of displacing fluid. Now, where was I? Yeah, in case of gas, let us take case of water first. This whole thing will become negative, so it will be 1 minus a. I am reducing all these parameters into one single equation. I am just talking about the sign change, or I can write it as x. So these whole terms are reduced into one single term, but since the density of water will be greater than that of oil, the difference will remain positive and there will be no change in effect of x, and I am writing this term as y. Now what will happen in case of gases? This thing will become negative. Density of gas minus density of oil is negative. Negative will get cancelled out, and you will obtain 1 plus x divided by 1 plus I. So what you can see, that fractional flow is higher. We can make a general statement. Depending upon the cases, the situation can be different, but we can generalize that fractional flow of gas is higher than that of water. So that is why we usually prefer water flooding process. This is something which is not that widely used